Swayam Prabha. Digital India. Educated India.
Again, welcome to the course of structural biology. We are continuing with the module of protein. Today in this class we will talk more about dihedral angle, peptide bonds. We have already discussed about peptide bond. We will go into the detail and we will learn Ramachandran plot, which have very critical role in determining protein structure. I talked about hybridization. Remember, I talked about hybridization is of three type, mostly commonly in carbon it is sp3, sp2 and sp. We talked about sp3, there is one electron from 2s orbital, 3 electron from 2p orbital, they hybridize to make 4 sp3 orbitals and they form a tetrahedral with an angle of 109 degree 28 minute. For sp2 they take one s electron and 2 p electron, so 3 sp2 orbital and 1 p orbital. These 3 orbital from 3 sp2 orbitals in the hybridization. So, this is sp2 hybridization. The sp2s are forming single bond and p orbital is forming pi bond, the second bond. Here the angle change from 109 degree to 120 degree. Then in sp we have one s and one p orbital forming 2 sp and there are 2 p orbitals which are forming 2 pi bonds. The angle is 180 degree. When we are talking about protein, mostly what we need is sp3 and sp2 hybridization. Remember, I told when hybridization made, I compare hybridization with khichdi, the hodgepodge. So, you have rice, you have pulse, you mix it, you get hodgepodge, and when you have taste that, you get the taste of rice, you get the taste of pulse, but you cannot separate them. Similarly, in hybridization you see the effect of s orbital, you see the effect of p orbital, but you cannot separate them. And more interestingly, why I am repeating this concept now, when you have sp3, sp2 and sp, I compare it, let us say s is pulse and p is rice. So, you take one bowl of pulse and 3 bowls of rice in sp3. You take one bowl of pulse and 2 bowls of rice in sp2, you get one of each in sp. So, if you do that in khichdi, you will see that taste change. Similarly, here also sp3, sp2, sp, they change their chemical characters. Another important thing which is very valid for protein is when they are sp2 hybridized, they are in same plane. That same thing you will see here in the peptide bond, which is involving a carbon, a nitrogen and an oxygen. Here they could form sp2 hybridization and they could form the sigma and pi bond. That pi bond is delocalized between the oxygen and nitrogen. So, you get them into same plane, and what we discussed earlier, you get the character being partial double bond. So, we will talk about this, the peptide bond, which you see the amino acid 1 and 2 join and they form the dipeptide. The joining of two amino acid result in the formation of a dipeptide. The carboxyl group of the dipeptide, now it is known as carboxy terminus, because in starting site it is N terminus and elongated, the new site is a C terminus, there is a carbon is available for the formation of a peptide bond with another amino acid. So, it continue like that. So, this is the growth of the peptide, and when it happened, three amino acid connected by peptide bond is referred to as tripeptide. Next would come tetrapeptide and so on. Polypeptide or peptide is a general term for any such polymeric molecule of non-defined length, and a protein is generally a long polypeptide. There is no clear distinction of when a polypeptide might become a protein, but in general when people talk about peptides, they mean short polymers which is 2 to 50 amino acids. More than 50 amino acid we call it protein. The peptide bond looks like it is a single bond and therefore free to rotate. However, as we talked about, the peptide bond has partial double bond character due to the resonance structure. You could see the resonance structure contribution here. The resonance structure have the following consequences. One, rotation around the peptide bond is restricted by 88 kilojoule per mole energy required to rotate. Therefore, it can be considered rigid. The carbonyl oxygen is positioned trans to the amide hydrogen. I talked about when there is a formation of double bond, the R groups want to be in distal position, and that is done by positioning the carbonyl oxygen trans to the amide hydrogen. The amide nitrogen valence electron geometry has some sp3 character and is therefore intermediate between the tetrahedral and trigonal planar. The OCNH atom in the peptide bond are usually considered to be coplanar. So, what we are talking about, that as I told there is a delocalization. So, originally it was a sp3 hybridized, but it also have character of sp2. So, it is an intermediate. When it is sp3 hybridized, it is tetrahedral. When it is sp2, it is trigonal planar. There is also a positive charge on the amide nitrogen which is plus 0.28 and a partial negative charge on the carbonyl oxygen which is minus 0.28. Now, what we are going to discuss is very critical. As I repeatedly talk about, our journey is from the sequence with the next generation sequencing. We have get number of sequence, and now from sequence we want to get function, the intermediate structure. The concept we start discussing here have a huge role on determining the protein structure. So, while the peptide bond is rigid, there is a single bond between the C alpha and C atom and N and the C2 alpha which are free to rotate. So, one is C alpha C. So, when you say C alpha C is C, so psi bond, and C alpha N is phi bond. As a result, while the C alpha CO NH C alpha 2 atoms are all planar, this planar peptide bond has 2 degrees of rotational freedom. These two rotational angles are known by phi and psi. Psi is the rotation angle about the C alpha C. As I told, when you say C alpha C, you say C is psi. Phi is the rotation of N and C alpha second, the next one. These are also referred to as main chain rotational angle. It is these 2 degrees of rotational freedom, very important, that allows the polypeptides to fold up into unique conformation. I repeat, it is these 2 degrees of rotational freedom that allows polypeptides to fold up into unique conformations. We talked about the difference of protein with other macromolecule. This is where they are differentiating. They have the junction connected, partial double bond, rigidity, and because of the rotation 2 degrees of freedom along with the phi and psi, they take unique conformation. So, each of the protein have their unique 3-dimensional structure. And that brings me to the concept of dihedral angle, again a very important concept. A dihedral angle is the angle between two intersecting planes. As I say, it's a angle between two intersecting planes, but I realize that it is not straightforward as understanding like normal bonds or angles. So, this is a dihedral angle, but when I say it is difficult to differentiate with the normal angle. So, I try to put some more discussion. If you look around, you will see in the place you are sitting, there are walls. So, if you look at the connecting wall, you see that there is wall A and wall B connecting, right? Now, if you have one point here, in this you have one line and in this you have one line. The angle between them is the perpendicular coming from this line and perpendicular coming from that line, where they are intersecting, making a angle. That angle is called dihedral angle. If you see here, you will get the idea little bit more clear. But from here, I will shift to somewhere in the atomic description of dihedral angle, which I hope will give you much better idea. It is also called torsion angle tau. So, what is torsion angle? It measures the orientation of 4 linked atoms in a molecule A, B, C, D. If you see this molecule, the angle created by them is called the torsional angle or dihedral angle. Tau ABCD defined as the angle between the normal to the plane of the atom ABC and normal to the plane of the atom BCD, which means if you see this, now you will understand. In this, it is called eclipsed or anti and syn, and this is called gotch or staggered. So, when you have this head to head, the theta equal to 0, they are called eclipse or syn, and when you make a 60-degree angle, it called staggered gotch. Now, I have given a link. Here is a beautiful video which will help you understanding how a dihedral angle is measured. You could see that for your reference, but I will do that in my way. So, if I put it like that and changing the angles, so this is anti, where they are in opposite direction, okay, but and this rotation is called the rotation of the torsion angle. If you remember, I talk about 3 secrets in the covalent bond: chirality, conformation, configuration. This is called conformation, where you get this structure and this structure without breaking any bond, only by using the operation which is called rotation. Remember, just in the last slides when we were discussing about the peptide, we talk about phi and psi giving degrees of freedom, which is rotational degrees of freedom because of this. Okay. Now, one thing you could have understood, here we have carbon with 3 hydrogens, right? So, if you put it like this or this, you don't get much difference in the energy. First of all, how this thing, what I am showing you, would be projected in your paper. This is called the Newman projection. If you see, these things could be drawn in such a way. This is the front carbon with hydrogens, and this is the back carbon with the hydrogens. If this is called syn, the other one would call anti. So these are two conformers. Clear? So the different spatial arrangement of atoms in a molecule which are readily interconvertible by rotation about single bonds are called conformation. So these and these, they are readily convertible. So the different spatial arrangement of atoms in a molecule which are readily interconvertible by rotation about single bond, so about a single bond, are called conformers. Syn and anti are conformers. Conformations represent conformers which are readily interconvertible by changing their dihedral or torsion angles. This angle, you see, here it is not touched. These angles are called torsion angles. Newman projection, it is also called Fisher-Newman projection. Formula for different conformations of ethane. This is ethane. When an ethane molecule rotate about its carbon-carbon single bond to extreme conformation can result in the staggered conformation and the eclipse conformation. That is I was talking about. This is ethane. You move it, you get a different conformation, syn and anti. The staggered and eclipse is the 60-degree rotation. Here I make a 180-degree rotation. So you get syn and anti. Okay, you understand it? So we are going to the next one, which is torsional strain. We understand the torsional angle or dihedral angle. Now we will go for the torsional strain separating the conformers. Torsional strain is also called eclipsed interaction strain. Strain that arises when non-bond atoms separated by 3 bonds are forced from staggered conformation to an eclipse conformation. So what it is talking about here, you have not a lot of differences because all are small. Instead of this difference, if I put a methyl group here, so there is a methyl group and here is another methyl group. Now if you see, when they are seen, there is a steric class, and that's why this conformer and this conformer are energetically different. This conformer and this conformer are energetically very different. So conformational energy barriers and energy minimization. So I will not go for energy minimization, but I will introduce the concept of energy minimization here. Butane, this is butane now, right? 1, 2, 3, 4, right? It's butane. How it could be presented? It could be presented in such a way. Here would be CH3, H. If this is syn, then this, and with that here. So this is the Newman projection. You have seen gauge, eclipsed and anti, 4 conformers. When we look at the chemical structure of butane, we can see that it has 2 substituents which are methyl group attached to the 2 end carbon atoms. Each conformer is also interconverted to the same forms by rotating the isomer around the central carbon single bond. So, how the conformer should happen? This, you have this, what is and now it would come here. So, syn, gauge, eclipse and anti. Interestingly, if you now put them, the angles starting from 180 to, you rotate in this way, so you get 120, 60, 0, 60. In that way, you plot it with the angle which is dihedral or torsion angle with energy. You get this at, so this is anti, this is the minimum. So, this is called global minima. This is another minima, this is called local minima. This is also local minima, and these are maximas. So, what you learn from here, that this is only butane containing 4 carbons, but by changing their relative position, you could get them free from the steric classes, and that make each of the conformer in different energy states, which give rise to maximas and minimas. So, if you have the molecule here where there is possibility of maximum strain, and you make it converted to this where minimum strain is there, you are actually pushing it from highest energy to lowest energy. The process by which, or you develop a code by which a computer would do this process, is called energy minimization, because from a high energy conformer you convert to a low energy conformer. But now I want to tell you few things, like if you have replaced them with different molecules like this and this. So, now these base carbons are having 2 heavyweight replacement, like in 2 positions, then it become even more complicated, right? Also, instead of doing this, if you do a separate thing, like you have attach, let us say, oxygen molecule along with a nitrogen molecule. Now they are heavy atoms still, but they might be happy in their syn conformation because there is a possibility of hydrogen bonds. I am not saying this is obvious, but it is also another complex possibility that they could love to form this hydrogen bond and want to stay in syn conformation. Because of this hydrogen bond, they get extra stabilization. So, in summary, we have just talked about starting from a ethane molecule where 2 carbon is there, change it by replacing another 2 methyl, getting a normal butane, develop an energy profile and replace by other groups, and see that in the limitation of all these 6 relatively heavy atoms like carbon and all, there are already development of complex situations, there are already developments of local minima, local maxima, global maxima, and all these things. First of all, we understand the conformational stabilities, conformational energy barriers, the different conformers which we could achieve by rotation. But more importantly, we could also imagine how complex it would be for a protein where many of such carbons, nitrogen and oxygens are together, and every one of them have their own rotational freedoms. So, we will come to torsion angle which are present in protein. So, this is a peptide where we see that the CN bond which is phi angle, the C alpha bond which is the psi angle, the C alpha N bond which is the omega angle, and the C alpha R which is the chi angle. The range of angle rotation for phi is plus 180 to minus 180, psi is plus 180 to minus 180. Omega is 0 or 180 and chi is plus 90 to minus 90. Who is chi? Chi is very important. As we are talking about 2 degrees of freedom. We are considering the main chain of the peptide backbone, but chi's are angles which are associated with the side chain. For example, if you consider glycine, there is only 1 hydrogen, whereas if you consider alanine, there is a CH3 group. You consider a aspartate CH2CO2H, for glutamate CH2CH2CO2H. So, in that way, with the difference in the amino acids, there would be different distribution of chi angles which would have their individual effects on the movement of the backbone. So, this is phi and psi which we are going to talk. So, this is the rotation of phi and psi, and when you look at them, you could easily see that there are restrictions when steric clashes happens. So, bond rotation determines protein folding, as I talked, and the unique 3D structure of the protein. Torsion angle tau in protein, 3 repeating torsion angle along protein backbone, omega, phi and psi. Omega angle tends to be planar, 0 degree for cis or 180 degree for trans. Generally it is trans, so it considered as 180 due to delocalization of carbonyl pi electrons and nitrogen lone pair. Phi and psi are flexible, therefore rotation occurs here. However, phi and psi of a given amino acid residue are limited due to steric hindrance. So, steric hindrance which takes a very critical role, interference to rotation caused by spatial arrangement of atoms within molecule. When they are rotating, if they come and do the clash, that is steric clash, and that make the rotation disallowed. Atoms cannot overlap. Atom size, how they will do that, it depends on the van der Waals radii. The electron clouds repel each other. So, omega angles tends to be planar, as I told, 0 degree for cis or 1 degree for trans due to the delocalization of carbonyl pi electron and nitrogen lone pair. Along the rigid structural backbone, psi and phi are flexible, therefore rotation occurs there. However, they are restricted because of the steric hindrance coming from the amino acids, which means the rotation and the spatial position of the atomic residues which are in the side chain, which are rotating with the chi angles. Very important now, only 10% of the phi and psi combinations are generally observed for proteins, first noticed by G. N. Ramachandran. We are very proud that this thing was observed first by G. N. Ramachandran and group, and they have worked on them and developed some principle which is called Ramachandran plot. So, phi and psi, the torsion angle phi measures the rotation around the alpha carbon nitrogen bond by evaluating the angle between the two neighboring carbonyl carbons when you are looking directly down the alpha carbon nitrogen bond into the plane of the paper, as I talked about. You see this, you will understand better. Conversely, the torsion angle psi measures the rotation around the alpha carbon carbonyl carbon bond by evaluating the angle between the two neighboring nitrogen atoms when you are looking directly down the alpha carbon carbonyl carbon bond, like this. Before going to the details, this slide represents a small biography and highlighted work of Ramachandran. You know, you all have heroes. In the film, we have Shah Rukh Khan, Amitabh Bachchan. In cricket, we have Virat Kohli, Dhoni, and all. So, this is my fan moment. This is my Amitabh Bachchan. So, I want the newcomer to know about him. This man was the only Indian to be nominated for Nobel Prize in Chemistry, had done immense impact not only in respect to Indian science, but in respect to international science. I have put little bit glimpses of his work here. So, for this work, what is Ramachandran's mode? They have developed models of small polypeptides to systematically vary phi and psi with the objective of finding stable conformation. See this line and you understand. In 1960s, it was not possible for them to look at the rotation of the entire protein. So, they have developed model of small polypeptides, and these models were very crude. They developed them by initially using cardboards and Proctor compass, they measured, and then they synthesized some of them. They developed computer models. For each conformation, the structure was examined for close contact between atoms. They measured all the details. Atoms were treated as hard sphere with dimension corresponding to their van der Waals radii. Therefore, phi and psi angles which cause spheres to collide correspond to sterically disallowed conformation of the polypeptide backbone. So, what they did, they take them, they did the rotation and see where the steric classes are happening or not happening. This is a Ramachandran plot. What you see here Ramachandran plot, what they did, they make a plot of phi versus psi. So, phi from minus 180 to plus 180 in the x axis and psi in the y axis, again minus 180 to plus 180 in the y axis. It is a 2D plot. Some combination of torsion angles are much more likely than others. They have calculated them out. The computed angles which are sterically allowed fall on certain regions of the plot. It shows frequency of phi and psi observed for residues in the folded protein. F and Y, actually this is a like representation of phi and psi. So, when you consider glycine, you see because of the less steric hindrance of side chain being only hydrogen, you get the plot mostly everywhere when you consider glycine. It would be very interesting when we put proline, because if glycine is the smallest, proline is definitely not the bigger, but because of its locked chain, it shows some restriction. So, proline's phi value is somewhat fixed by its side chains bond to the backbone. See, it is fixed. So, it is only in one axis, and other axis you do not see the change. So, this side chain can clash sterically with the preceding amino acid. So, the pre-proline Ramachandran plot is also unique. Try to understand that. Proline, it locked, so the residue before proline would also be interesting. But before that, I just want to show you, this is glycine, this is the plot of gly, and this is the plot of pro, and you get the clear difference. This is pre-proline Ramachandran plot. You see movements, but still you see restrictions. This is, so this is pre-pro, this is pro, and this is glycine, and the difference is very clear. Another very interesting trend in the Ramachandran plot, if you see, this is the position of amino acid, let us say N, the N plus 1th amino acid would be very close to that. So, there is a correlation of their position. So, what do we get if we repeat the same torsion angle many times in a row? So, let us see that. So, we put a polypeptide chain which actually shows the trend to be restricted in the green highlighted region. That is the alpha helix. So, this amino acid chain participate in the more common right-handed form of helices. So, if it is coming here in the phi psi plot, Ramachandran plot, it is representing the secondary structure alpha helix. So, now from amino acid we are shifting to the polypeptide, we are understanding the correlation, we are understanding the positions. The other right-handed helices which we talked about, the 310 helix and pi helix, they also have similar torsion angles. So, you see that they are in the same place. Then we put a different polypeptide chain, and it shows that when it goes in the other region, it is representing amino acids which are part of the beta sheets, be it parallel or anti-parallel. Now, the another region where we see there are clustering of plots, and these amino acids participate in the less common left-handed form of the helices. So, when we make a summary, we see that for alpha L comes in between phi 57, psi 47, the structure is represented left-handed alpha helix. For 310 helices, it is minus 49 for phi and minus 26 for psi, it is right-handed, we know. Pi helix minus 57 for phi and minus 80 for psi. For type 2 helices, minus 79 for phi and 150 for psi. These are left-handed helices formed by polyglycine and polypropylene. Collagen minus 51 for phi, minus 153 for psi, right-handed coil formed of 3 left-handed helices. So, if you see here, this is the plot. As I told, the plot is made by putting the phi in the x axis and psi. If you see, this is phi, this is between this C and N, and this is between C alpha and C. C alpha and C is psi, which is put in the y axis, and C and N put on the x axis. Now, this portion which is here highlighted, this is right-handed alpha helix. So, if the amino acids would be a part of the right-handed alpha helix, they mostly cluster in this region. If they are part of the parallel beta sheets, they are part of this region. If they are part of anti-parallel beta sheets, they are part of this region. If they are part of collagen triple helix, they will be part of this region. If they are part of twisted beta sheets, they would be part of this region. And if they are part of left-handed alpha helices, they would be part of this region. So, we have started our journey from the understanding of the peptide bond, the torsion angle, where the hybridization happened, how this hybridization make the things rigid and planar, and with this planarity the associated bonds which are phi and psi are rotating, and how their rotation are restricted by the influence of the individual amino acids, their side chains movement by different chi angles, and because of that how glycine and proline we have seen have very differently projected in the Ramachandran plot, and now we see when they are forming alpha helices or beta sheets how they are putting themselves. We could also understand Ramachandran plot and energetics. So, according to specific dihedral angle and their range, there is a particular energy state. So, because of the rotation, they would be in a sterically allowed position, and that rotating state, that state where they are, the conformer state, have its own particular energy state. Stable state are designated as per the low energy level indicated by blue patches, which you will see here. The blue patches are showing the low energy state. The lowest energy state can represent the reference structural contents, motifs or domains in protein based on which 3D structure of other proteins could be validated. Very interesting point. So, the lowest energy state represent the reference structural content. You already have a lot of already established structure in the protein data bank. So, you get them, you calculate their position in the Ramachandran plot by calculating their phi and size, plot them and calculate their energy. This would be very interesting and very informative as a reference for validating a new structure. Also, if you see the story of the glycines here, it is the same glycine tripeptide and they convert between two different forms. So, by rotation they convert in two different forms, they are giving two conformer, and hence they are positioned on the different part of the energy state in the Ramachandran plot. According to flexibility present in the bonds involved in the dihedral angle in protein backbone, different level of rotation can be observed in protein secondary structure content. Depending on the rotation in protein secondary structure content, the stabilization energy also differs. So, when you see that, you are considering those secondary structure, it's alpha helix and I think beta sheet. So, individually when you are considering alpha helix, what they have, they are stabilized by N to N plus 4 C double bond O in H bond. So, they are internally stabilized. So, as an individual unit, alpha helix represent most stable secondary structure. But now you see the energy profile, and you argue with me, you told that alpha helix is the most stable, but I see that this beta sheet is better, right? You see that this is because this is beta sheet and not the beta strand. Can you understand what I am saying? So, beta strand individually have no ability to stabilize themselves through hydrogen bonds. So, they bring, so one beta strand bring other beta strand, be it the parallel or anti-parallel. So, they are together and together they are having more energy. Is it clear? So, individually one alpha helix is having better energy, it is more stabilized, but beta strand could not be staying together. You cannot measure a single beta strand. So, you have to measure the total beta sheet, and as a sheet they are having more energy than alpha helix itself. Coming to dynamic Ramachandran plot, which is a modification, modern modification. So, dynamic Ramachandran plot represent the conformational changes in protein structural content in respect with the modification in the dihedral angle values. Here, if you see in this plot, this is also a Ramachandran plot with the change here. You see the changes in the peptide, and you see P2, which represent a portion of a twisted beta sheet, gradually changes into right-handed alpha helix, has been demonstrated through sequential intermediate indicated by this to gamma to H to beta to alpha. So, when you are changing a structure, the same structure have changed its state and changing from a twisted beta sheet, this is a twisted beta sheet, to a right-handed alpha helix. So, this journey is reflected by having points initially starting from this P2, coming to this gamma state, coming to this H state, coming to this B state, and ultimately coming to the right-handed alpha helix. So, when you go for dynamicity, which we could see in this course, I have a small portion, I will talk about the dynamics. So, you have a structure, you have its force field, and you have a equation for the force field which is influencing the bonds. You put a force and gradually it would be changing its state, and it would have a journey from the twisted beta sheet to the right-handed alpha helix, and that journey could be reflected in a dynamic Ramachandran plot. So, Ramachandran plot for model validation. Before I talk about, I want to show you this secondary structure of protein. If you see that, you will see that alpha helix here, you will see 310 helix there, you see beta sheet here, you see anti-parallel beta sheets here and loops here. So, this is a protein which had many secondary structures, and taking that we are going to validate it. What is mean by validation? Remember I was talking about, so now there are many experimentally solved structures. By taking that experimentally solved structure, putting them into Ramachandran plot, now we know that which 3D conformer, what type of this torsional angle distribution are representing a valid structure. For example, if you see this structure, when we plot the torsional angles, 286 amino acid residues among 304 residues are plotted within the preferred region, which is 94.08% of total protein content. What is a preferred region? So, as I told, if you go to the protein data bank, you will get the experimentally solved structure, which are experimentally solved structures, so they are validated structure. The torsion angle distribution of amino acids are calculated, they are clustered, and from this cluster we have developed a preferred zone which is favored, and then after that it comes to the allowed region, and then it comes to the outlier or disallowed region. So now we have this standard database, and for a new structure we are plotting its torsional angles and calculate the preferred region, allowed region, and outliers. So if you see in the above structure, I told among the 304 residues of the full length, 286 amino acids are plotted within the preferred region, which is 94.08% of the total protein. Allowed region, there is 15, which is 4.93%. In the outlier, there are 3 which represent less than 1% or 1%. This higher percentage represent that maximum residues are able to form the compact secondary structure and tertiary component of the protein. According to Ramachandran plot and its statistics, the protein structure is highly valid. So up to now I was talking about plotting. This is what a wonderful application of Ramachandran plot. Remember, we start this course to putting the problem in front of us, where we have through like next generation sequencing a lot of sequences. So DNA sequences which would be easily converted to protein sequence. Now we have to convert this protein sequence, getting function out of that, and which needs to understanding of the structure. But unfortunately, through the next part of the course we will discuss, I have given you some glimpse in the last module that how these structure solutions are extremely critical, how they are expensive and time consuming. So a gap is there and it is very difficult to bridge the gap. But one easy solution, not a optimum solution, easy solution is to do predictions, predictive models by using computational biology method. But when you are doing prediction, you need a validation, and here Ramachandran plot is working, doing an amazing job, so that it gives us confidence to the model that this model is validated. So the importance of Ramachandran plot in validating protein structure is extremely useful in validating experimental structures. That is one thing at the earlier stage. Now the technique is used more importantly to validate predictive models using modeling techniques like homology modeling, fold predictions, etc. I would finish this chapter, today's class, by saying that, and I am very proud to say because he is my hero, the best part about Ramachandran plot is it was developed in 1960s, 70s, but even today it is still valid, competing with the other supercomputing based or artificial intelligence based prediction validation tools. Till today, your model you need to validate, you have to go for Ramachandran plot and do the validation based on them. So it is that important, it is that critical, and now you think about a innovation done in 1960 to, like it's actually 69, but the work done 60s, 70s, which helped the entire world initially to solve the initial protein structures. But even now we are taking help of this plot, this technique, towards the validation of predictive model. Thank you very much. In the next class, we will continue this concept towards understanding the super secondary structures which are also critical in development of structure or understanding function. Thank you.